In this video, we're going to learn about direct variation and partial variation and how to identify the difference between each of them. In this first example, we're being told that Carly is driving to Montreal at 60 kilometers per hour. And we're being asked to fill in a table of values to show her distance as time goes on, up to 10 hours. And then once we have that table of values, we're going to graph the relationship and we're going to label the independent and dependent variable on the axes. So first we're going to fill in our table of values. So our independent variable is time in hours, and our dependent variable is distance in kilometers. So at time 0, she has gone 0 kilometers. After 1 hour, she's gone 60. After 2 hours, she's gone 120. After 3, she's gone 180. After 4 hours, she's gone 240. After 5 hours, she's gone 300 kilometers. After 6 hours, she's gone 360. After 7 hours, she's gone 420. After 8 hours, she's gone 480. After 9 hours, she's gone 540. And then if we went all the way to 10 hours, we ran out of boxes, but she's gone 600 kilometers. Okay, so now we're going to graph that information. So our y is our dependent variable, so that's the distance in kilometers. And then our independent variable is time in hours. So we are going to go up by 60 kilometers each time. So 60, that would be 120, 180, then 240, then 300, and so on. And then our time in hours is going to be just 1, 2, 3, 4, 5, 7, 9, and then that would be 11, and so on. So every line will be 1 hour. So now we're going to plot our information. So at 0, time 0, we've gone 0 kilometers. After 1 hour, she's gone 60. After 2 hours, she's gone 120. After 3, 180. After 4, she's gone 240. After 5, she's gone 300. After 6, she's gone 360. After 7, she's gone 420. After 8, she's gone 480. After 9, she's gone 540. And finally, after 10, she's gone 600. So if we had labeled that whole thing there. So we can see that it's going up in a linear fashion. I'm going to draw a line of best fit, like so. And there we go. So there are some questions to be considered. So the first question is this relationship linear or nonlinear? And it's linear because it's going up in a straight line. And where does it cross the y-axis? It crosses the y-axis at the origin, or 0, 0. And another thing it's asking us to do is to write an equation to find the distance she traveled after t hours. So if we were to write this as an equation, d equals 60t, because for every hour she's traveled, we will know she's gone 60 kilometers. So use the equation to determine how far she could travel in 15 hours. So what we're going to do is put in 15 for t. So d equals 60 times 15. That's equal to 900 kilometers. So one thing to note is that it's way easier to plug a value into the equation and it's much more efficient than to draw out a graph all the way up to 15 hours, because we would have had to keep plotting points or keep adding things into our table of values. So writing an equation and then plugging in the missing value is way easier. So the example that we've just worked through is an example of direct variation. Another way to say this is that one variable varies directly with the other. So in direct variation, you're going to have a linear relationship, and it's going to pass through the origin or through 0, 0. The next examples we're going to look at will be a little bit different. So direct variation occurs when the ratio of the variables does not change. So in other words, when the dependent variable is a constant multiple of the independent variable. So this is how we algebraically can represent direct variation. Y equals mx. So a few things to note here. M is the slope. And this is also known as the rate of change. And the other thing that we have to note with direct variation, that the graph passes through the origin, which is also known as 0, 0. So there's two key parts to direct variation. The graph has to go through the origin, and it has to go up by the same rate. Okay, so we're going to do a couple of examples where we will solve to find the slope or the rate of change, which is also represented by m. So the first one, the distance traveled by a car varies directly with time. The car travels 270 kilometers in 3 hours. So we need to find out what the rate of change is. So m is equal to the rise over the run, or the dependent variable over the independent variable, or y over x. So in this example, we've gone 270 kilometers in 3 hours. So that is equal to 90 kilometers per hour. So that's our first example. In another example, we're being told that the total cost varies directly with the number of games bought. 8 games cost $480. So this time, slope is going to equal $480 divided by 8. And that's going to equal $60 per game. So each game costs $60. So slope is another way of looking for the unit rate. So we practice those at the beginning of our course, calculating unit rate of change. This is the same thing. It's just called slope now. It's still the rate of change, or the unit rate. So in our next example, we're being told that Chris works part-time and he earns $7.50 an hour. So we're first being asked to describe the relationship between his pay and the hours he works. So we can say that his pay varies directly with the hours. For every hour, he earns $7.50. So if we were to write that into an equation, we would say, remember, we have to put it into the y equals mx format. So y equals 750x. So he's making $7.50 an hour. Another way you could put it, if we wanted to represent, so his P equals 750 and then times that by the hours, that would work too. So our next one, we want to find out if he makes $78.75 in a week, how many hours did he work? So we can plug in our information. So y equals 750x. We know that he made 78.75 equals 750x. We want to find out how many hours, so what x is. So we need to divide both sides by 750, and that will give us x. So these will cancel out over here. So we have 10.5 equals x. So that means that he worked 10.5 hours that week. Now we're going to take a look at partial variation. So with partial variation, our graph is not going to pass through the origin. Instead, it's going to hit the graph along the y-axis somewhere because there's going to be an initial value involved. So in this example, we're going to say that a large pizza costs $6 plus $2 for every topping. So we're going to fill in a table of values here. So n is going to be our number of toppings, and that's going to be on our x-axis. And then c is our cost in dollars. That will be our y. That's the dependent variable. The cost is depending on the number of toppings. So if we didn't get any toppings at all, it's going to cost $6. If I get one topping, it's going to be $2 more, so it'll cost $8. If I get 2 toppings, it'll cost another $2, so $10. 3 will cost $12. 4 will cost $14. And 5 will cost $16. So now we'll put that onto our graph. So our dependent variable is cost, so that'll be on the y-axis. So cost in dollars will go there. And then on the x-axis will be our number of toppings. So I'm going to go every 2 dashes will be 1. Like so. And then along the top, I'm just going to make every dash 2. 2, 4, 6, 8, 10, 12, 14, 16, 18, and so on. So now we're going to plot that. So with 0 toppings, it's going to cost $6. With 1 topping, it's going to cost 8. 2 toppings is going to cost 10. 3 toppings is going to cost 12. 4 toppings is going to cost 14. And 5 toppings is going to cost $16. And now we can draw our line of best fit, like so. Okay, so now we'll answer a few questions. So first of all, is this relationship linear or nonlinear? It's linear because all the points line up quite nicely. And it passes through the y-axis at 0, 6. So you can see that right here. It's not passing through the origin, it's passing through at 0, 6. And our next question is to write an equation to find the cost of a large pizza, C, with n toppings. So we're going to say the cost is equal to 2n plus 6. So the plus 6 is our initial value. We use that to figure out what our base cost is, and then we know that if you've got 0, we plug that in. So 2 times 0 would be 0 plus 6, so that would work. We would have $6 for the first pizza. So then our next question is, how much would it cost if you were to get a pizza with 8 toppings? So if we put that in, so 2 times 8 plus 6, it's going to cost $22. So this relationship is an example of partial variation. So in partial variation, if y varies partially with x, the equation is of the form y equals mx, just like before, but now plus b. So b is the y-intercept. It's also sometimes called the initial value. And then m is still the slope, which is also the rate of change. So another way of describing partial variation is the graph of a partial variation is a straight line. It's still linear, but it doesn't pass through the origin or 0, 0. Instead, it passes through somewhere along the y-axis. So now we're going to work through an example. So we've been given a partial table of values. So we don't have all the values written in. We're being told that this table of values shows that y is varying partially with x. So that means it's not going through the origin. So if we take a look at x when it's 0, y is equal to 4. When x equals 1, y equals 7. So x went up by 1, y went up by 3. So that means that each time y is going to go up by 3. So let's fill in our missing values. So when x goes up to 2, it increased by 1, y is going to increase by 3, so 7 plus 3 is 10. And then 13 is going to increase to 3 by 3, so it's going to be 16. Now we're going to graph the relationship. So along the bottom is our independent variable, or x variable. This is our x, this is our y. So I'm going to make every line equal to 1. 1, 2, 3, 4, 5, and so on. This one I'm going to go up by 2. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, so on. So I won't put all the values in, but you get the point. So when x is 0, y is 4. So it's going to be right there. When x is 1, y was 7. So we've got 2, 4, 6. It's going to be about there. When x is equal to 2, y was 10. So that's going to be right there. When x was equal to 3, y was 13. And then finally, when x was 4, y was 16. So right there. So that is our graph, and we'll draw a line to show that it's a linear equation. So now some of the questions that we're asking. What is the initial value of y, or the y-intercept? That is 4. So the y-intercept is 4. So it's 0, 4. What is the constant of variation, which is the rate of change, which is also the slope? The constant of variation is 3. M equals 3. So b equals 4. M is going to equal 3. So write the equation in the form y equals mx plus b. So it's going to be y equals 3x plus 4. That is our equation of this line. So now we're going to go through some examples of EQO questions that involve direct and partial variation. So in our first example, we have a bus is rented for a class field trip. The transportation cost for the trip is made up of $225 to rent the bus, $50 for gas, and then $2 for each bus seat. So, which relation below describes the total transportation cost for the trip if C is the total cost in dollars and N is the number of seats? So one of the best strategies for solving an EQO question or any multiple choice question is to cover up the solutions, or don't look at the solutions at all, and try to answer it yourself on your own. So first of all, there are two things that are adding up to the initial value. So we have the $225 to rent the bus, and then $50 for gas. So that adds up to $275 initial value. And then it's $2 for each bus seat. So our answer is going to be C equals 2N plus 275. So let's look and see if that is an option. So it is. If we look down at the last option, C equals 2n plus 275, so it's D. But let's just take a bit of time and talk about why the other ones are wrong. So we can actually get rid of these two altogether, A and C, because the initial value, the B, was 225. So that was wrong. So it had to be B or D. But then if you take a look, we have a negative number here. So it's not going down for every person that rides the bus. The price is going to go up. So it wouldn't be negative. So we can get rid of that. So it does leave us to the choice that we did select, because we have C equals 2n plus 275. In our next example, we have a computer is expected to decrease in value over time. The relationship between the value V of the computer in dollars after T years is written as the following. So V equals negative 300T plus 2100. So a line representing the relationship is graphed. So we have it going downwards. So that makes sense. We have a negative slope, so it's going down and to the right over time. So it says, what does the V-intercept of the line represent? So if we take a look here, the V-intercept would be the initial value, what you start off with. So it's not the first one. It's not the decrease in value per year, so that's wrong. The initial value of the computer, that is the right answer, so it's that one. It's not the number of years until the value is 0, that's wrong. The V-intercept is over here, so that's when time is 0. And then the number of years the computer would work, this graph is nothing about that at all, so it has to be G. Okay, in our next one we have a table of values representing a linear relationship. And the question is, which equation represents this relation? So let's take a look here. So we have at time 0, distance is 5. Okay, and then at time 1, it's 15. At distance 2, it's 25, and so on. So if we take a look at how much each time it's going up, when this goes up by 1, this is going up by 10. And then this is going up by 10, and so on. So our first difference is 10. So the question is, which equation represents this relation? So it is going to be D, and our slope is 10. It's going up by 10 for every 1. So it's going to be 10t. And then we need to figure out, okay, so is there an initial value? There is an initial value. It is D. So the correct answer is 10t plus 5. So the answer is C. It's not direct variation, so we can get rid of these two because there is that initial value of 5. And really, if you know the initial value is 5, you didn't have to do any of the figuring because there was only one that showed the initial value of 5. So in our next example, we're shown a graph, and it says it's showing the cost versus the number. And the question is, which of the following describes a difference between lines 1 and 2? So the first statement says line 2 has a larger initial cost. Well, no, the initial cost for both line 1 and 2 is 200, so that is false. Line 1 has a larger initial cost. Well, if line 2 doesn't, then line 1 can't either. Line 2 has a greater rate of change. That is incorrect because line 2 is less steep than line 1. So the only answer that can be correct is D. Line 1 has the greater rate of change.